So first of all, thanks a lot for the support and feedback you provided for the last two videos of this series. So let's go right ahead. In the previous video, we saw how to hack processes by changing the process memory. But the processes we conjured thus far were just toy examples whose internal workings were well known by us, and its state was even captured conveniently in an endless loop. The spam program was written merely for a proof of concept, firstly as a sandbox for ptrace and for its use through a Lisp system. But the processes that we'll encounter in the real world won't necessarily make their internal workings known to us by being open source. We'll have to reason about them given their inputs and outputs. How then should we find in the process memory the data we care about? So let me introduce you to our first game hack. It is an iteration of the Castlevania genre called Castlevania Aria of Sorrow. It's one of my favorite games, and as such it is overdue to getting hacked. It also constitutes our first black box process. So what do I mean by black box? Now, though we can look inside, as we can read any memory address we desire with peak data, the thing that is hidden from us are the inner workings of the process. What address value is responsible for what? What is it representing in the game? Also, we're starting with Castlevania because it is run in an emulator, so we have some powerful control over the process through the save state and save loading feature, such that if we make a blunder by poking the wrong address, we can simply reload a previous save state, making this actually a suitable stepping stone before embarking on more difficult hacks. So let's actually hack some games, right? So again, we divide the screen conceptually. Left we have the tracer, on right we have everything associated with the tracee. So here's our hero Soma, and we are playing this game Castlevania in an emulation. And the emulator is called Metnofen, so we can monitor it here. So the idea is we can check out this maiden. What's up? Nah, she beats the crap out of us. And now we can reload this state as if nothing happened. So we have some memory control here. And the idea will be, up left you see this 306, that's the health value. So you see on the red thing here, it's not completely full. So we will try to hack this health value, find it in memory and get Soma, our hero, back into good standing. So the problem is, well, let me quickly show something here, beating this maiden. You see this seraphim up here. If we were to attach to this process, pay attention to her moving wings, she will stop. So we have some nice feedback here when we try to stop processes, because the animation of the game also stops. So it's not bad to read some subtitles or whatever. Anyway, so you see the process status changed to traced again, and we can try to find our health value of 306. Now the idea here is we have to blindly search the process address space to find this value. So how big is actually the address space? So I'm running a 64-bit hardware with a 64-bit operating system. So the process can take up addresses from an address size of 64-bit. So that's addresses ranging from 0 to 2 to the power of 64. That's our exponentiation function. So this is how many addresses we would have to scan to find our 306, to find our health value. Now this is a huge number. This is a ginormous number. If we just were to loop without doing any scanning from over this number, or let's just loop over several less orders of magnitude, over 32 bits, if we were to measure how much time it would take to just loop over 32 bits, it would take 1.7 seconds. And you think, oh, that's not so bad, we could just some operation there will be 5 seconds or something, but we will scan 64 bits, so that's several orders of magnitude more. And to put things into perspective, if we take 1.7 seconds and multiply them by the missing 32 bits, it will take this many seconds. And that's a huge, huge number. So if we divide this by 60, we get minutes, 60 again we get hours, 24 we get days, months, years. So you can see it would take 246 years just to loop over 2 to the power of 64-bit 2 to the power of 64 addresses. So that's unfeasible. My computer will not run this long. My house will be demolished by the time I will grow of old age. So the idea here is, how can we cut down this 64 bits? How can we cut it down to something feasible so we can finish it in my lifetime? So how do we slay this 64-bit beast, this 200-year problem? Well, with the blade of knowledge. So the idea here is that the process memory isn't arbitrarily organized. It may start from 0 to 2 to the power of 64, but actually it is a lot smaller. So first of all, modern CPUs can't even address this much. They don't even do this in the background, hardware speaking. So we already are limited to like 48 bits last time I read Wikipedia. And of these lesser bits, there is also a division into kernel space and user space. And basically, so every process has to sacrifice some of its addresses to the kernel, so that kernel code is always addressable. It can handle all kinds of things like, for example, system calls like ptrace, and so on and so forth. So you already lose a big chunk of memory to the kernel. So what is left is the user space, and this is where the program is located and all the data needed to execute it. And the user space is actually subdivided into further regions in so-called memory segments, and there are 6 of these. And basically, the program, when the process tries to execute a program, it actually has all the data organized within its guts, within its memory space. So first of all, there is the text segment. So you can imagine it's like a book. So it's like a book, like a text in a book. It should be immutable data mainly, because herein we have the machine instructions. So all the executable code, and also string literals, and as in the first hack, our ABCD literal is also located in here. So that's when I was able to use the instruction pointer to overwrite the loop predicate, if you remember. So if we cut this out, so the next region, or let's leave it here, this was the text segment. The next region is the data segment and the BSS segment. So let's put them both together. They mainly store variables that are static. So if you think C, so it's static X. Uninitialized, they are stored in BSS, and if they are initialized in code already, so static data segment equals 2, then they're stored in the data segment. So if we think the health value, is it located in these? Well, probably not. We kind of take a wager here and say that the health value of Soma probably isn't captured by a static variable. And finally, we also have the memory segment, which is just the stack. The stack, you are probably familiar with this. So when we call functions x and y, then we kind of try to carry these around these arguments, and when we're done with the execution, we want to return to the return address, and the stack takes care of us. Among other things, it also like carries all around the frame with all its local variables and the environment and so on and so forth. It takes this heavy burden from the programmer. So the health value might indeed be located in here. So if there's, for example, some kind of damage function that takes in, I don't know, the health value, well, yes, and -10, so it reduces the health value. It might indeed be in here, but it would be pretty involved to chase around functions to find the stack, to find the health value in the first place. So we will not try to attempt to hack the stack. Not to mention that we also just had to kind of try to manipulate this black box process to get in a state where we can assume that right now in the stack the health value resides. So then there comes the next 2 candidates, and these are our winning candidates, the heap and the memory mapping. Well, let me look this up real quick. The memory post-production memory mapping segment. So these two store data that is created at runtime, that is allocated at runtime. So you think the C function malloc, and for this one the system call mmap. So the health value is probably being allocated at runtime. Not lastly, because we are running this in emulation, so pretty much everything is going to be. The heap is, as a rule of thumb, is being used for small values. So last thing I read was smaller than 128 kilobytes. This is programmable, so we can't really rely on this, but to get you an idea, whenever we allocate values of this particular size, they are probably going to be found in the heap. So our health value is a pretty small value, but you can imagine if the health value happens to be part of some kind of pointer to some player, and the player has all these fields for strength and intelligence and so on and so forth, that it might kind of become big enough to indeed become part of the memory mapping segment. So we will focus our hacking effort on the heap. So the last thing to take away here again from the memory mapping segment is that also when files are being mapped to a process, this is also done through memory mapping segments and a dynamic library. So for example, the libc library is also mapped through in the memory mapping segment, not through heap. So the question then becomes, if we don't use the memory mapping segment, if we don't focus on this for now, and we focus on the heap, well, what are the addresses that encompass the heap, right? So from what address to what address does the heap run? This is what we have to know in order to do the proper peak data call to query them. To a process, the kernel is the origin of space and time, of memory and execution. The kernel implements these laws of nature by modeling the process with internal data structures, capturing the state of a process so that it can stop and resume them and add memory and free memory at will. Now, this state representation of a process also encompasses the memory regions used by the process. We have access to those data structures through the proc file system located on Linux in /proc. Here, the process data structures can be read like a file system, where structs and slots are abstracted by directories and files. Here we can read out the memory mappings of a process, that is what addresses are mapped for most memory segments. Let's see for ourselves. So in order to find this, we use the procfs file system. So the procfs file system, see down here, is the programmer's interface to these kernel data structures. And to find the data structure for our process, we simply go proc / and then the process ID, so 25936. And so this is our proc file. And here, in the file maps, we can find the memory that is allocated by this process. So let me make this full screen, like so. So those are our memory regions. So here is the start address and the end address, and if it is readable, and all kinds of data. And we know that here's the process that we summoned for this. So these are all the memory regions that we care about. Now, where is the heap, and where is the addresses responsible? Where's the address encompassed by the heap, and where is the address encompassed by the memory mapping segment? So the heap is here. This is the only thing that you can find from this file easily. Now, the memory mapping segment, I will get to this later when we hack a more harder to hack game like Rogue Legacy. That's when we're gonna need it. But for now, we can concentrate on the heap. And the heap, we have here the addresses that make up the heap. So here is all the runtime data is located here, objects created at runtime, and so on and so forth. So we have a strong inkling that herein we will find the health value, because the health value is something that must be that usually has to be created at runtime, that needs to be changed continuously, and so on and so forth. So we can scan this address region. So we can look up how big is this address region. I don't know, let's post this here in. Use hexadecimal notation. Create the difference from these and the absolute. So those are just 1, 2, 3, 10 million addresses. So we can easily loop over these, like loop for e from 0 to this one instantly. And that's our first approach to this. Okay, so now we have our heap region. Let's try to scan over it. So let's quickly capture the heap into a list with the start address and end address, so we can loop over this. By the way, up right here, this is still our game, but because the game loop is not running, the graphics is not being updated. So if I detach from this, and attach from it again, you see the graphics is still here. So what we want to do now is, we have now the heap, right? And we have the addresses starting from this one to this one. We want to do peak data, look up the address, and see if the health value is stored within them. So let's quickly capture the health value here. It's 305 up right here. This is our health value, like so. And now I have a function written for this, a find value address, which takes a value like health and searches for it. This is a fairly powerful function. We can provide all kinds of ways to search for this, and we can provide it an address range. Which takes a list where the first element is the start address and the second one is the end address. So we will search in the address range of heap, and if I press enter, it will search over this entire heap region for the value 305 and go. So you wait a little bit, let's see how long it takes to search 10 million addresses, and we're done. So all these addresses are candidates. They could be the location of our health value. So now comes the next step. Here is a certain kind of heuristic, and you might know this from cheat engines. We will resume the game and change the health value. Before we do this, let's quickly capture this list. So with setf, let's call it sieve, and we will capture this list. So star refers to the last thing in the REPL, so that we have this first filter, so to speak, of where the health value might be. So let's resume a game. And now we have to imagine this seraphim is a helpful health arithmetic, which takes health. And let's attach to it again. So now our health has dropped from 305 to 285. So let's change our health value here to 285. And now let's scan over these addresses that we thought might be candidates to be our health value and see which one of these changed to 285. And this way we have strongly narrowed down our problem size. So let's find value address, our new health value, which is 285, and this time we provide an address list, so it will scan every address in the list. And this one, right, so it's our sieve, and go. And we have 3 candidates still. I already did some trial and error, and I'm pretty certain that the last value is going to be our health value. So let's poke our health value. Let's try to change the health value. Or rather, quickly let's do the sanity test and see if this is indeed our value. And it ends with 11D. Let's quickly ask what is 11D. This should be 285. Indeed, let's poke it now. So poke data. This address here. Back to, I don't know, let's change it to 66. Detach from the process. And let's see up here if this 415 changes again. And it changed, and it even has some animation to increase it. So the internal, I don't know, game engine sees that there's a new value, and it runs its incrementation animation. So it's pretty neat stuff. So we're successful. We hacked Castlevania. But we're not gonna stop there, right? Just the video is stopping here. So congratulations for making it through the video. The video just blew up, but I had to cover this concept in one video. It had to be coherent in one place. So I still wanted to do one more video where I will try to hack the game Rogue Legacy. It's a little bit more involved, and there are still some juicy concepts I want to cover. And yeah, if you don't want to miss it, go ahead and subscribe. Leave a like if you want to see more of these kinds of videos in the future, or if you feel like giving me some feedback, some suggestions, anything. I love to read it. Then just leave a comment. Oh right, and the code is available on GitHub. I'm leaving a link in the description if you want to try to work with my system. And with this being said, take care and see you in the next video. Bye bye!